Hey there, and welcome to the first series of lectures for astronomy and cosmology. So I hope you guys had fun watching the demo, the stellarium demo from the last video. So now in this session, we'll be looking at some of the more exam-oriented concepts, and we'll be answering most of the questions that we raised in the last video. So if I were to just write those down, so some of those questions were, how do you, or how do we, because I guess we're friends now, how do we estimate interstellar distances? How do we estimate the radii of planets or stars? And how do we estimate the brightness of some of these stars? So we looked at the demo last time. So that was not only just an estimate of the distances. If you looked carefully, then that app was also showing how the distances are changing with time. So that was in real time. So how were the distances changing? So that app was also showing that. One thing I forgot to show you, that app also shows many of the real satellites that are in motion about the Earth or any other sort of orbit. So for example, if I just take the names of Starlink, right? So Starlink satellites were also visible in that app. Similarly, other ones, for example, which are either for the purpose of just finding information, such as some telescopes. So those are also available in that app, and you can also look at other sorts of satellites which are used for imaging or some sort of military purposes and so on. So anyways, these were the burning questions that we imposed in the last session, and now we'll be looking at answering some of these. So first, obviously, no study of this chapter would be complete without mentioning our good old friend, the sun, right? So see this? So this is actually one of these solar flares that the sun actually emits. And I know that you just saw this height, but on the scale of this looks pretty small, but this is like almost the size of the diameter of the Earth, right? So this is how large this solar flare is. So let's quickly run through some of the concepts that we were discussing last time. So for example, we talked about the fact that stars and planets, the difference is stars are luminous bodies, right? And what I mean by this is that these produce their own light, right? So this means that they produce their own light. So for example, one of the best known examples of the stars that we have at our hands is obviously the sun. So they produce their own light. And based on the information that we studied prior to this unit, we also know exactly how the sun produces energy. Obviously, the importance of the sun to life on Earth cannot be overestimated. If there wasn't the sun, obviously we could not see anything on Earth, right? So we need some source of light to see. That's how vision works. And also the temperature on Earth would be very cold, not suitable for human survival. So we know that the sun produces some sort of energy, and actually this is not just a one-time source of energy, this is a continuous source of energy, at least for the near future, right? So we know that this source of energy needs to be fueled by something, and in the case of the sun, we know that nuclear fusion between hydrogen is what fuels the sun, right? So that's what causes it to consistently produce energy. So for example, if I know you guys have been listening less to me and focusing more on this animation, so you can focus on this sort of a dusty sort of hues that you can see here. So these are actually the plasma gases, right? So this is a plasma of the hydrogen gases, and this is what is occurring in the core of the sun, right? So at very high temperatures, this hydrogen is fusing together, and this is actually what is powering the sun. So now if we continue with the concepts that we're talking about, so something else we were talking about last time was galaxies, right? So what are galaxies? Galaxies are just collections of stars, planets, and many more celestial bodies, right? So in these many more celestial bodies you have you have meteors, you have comets, right? You have just clouds of gases floating around, and they actually form a gravitational field of their own. So that's all you have, and this is what galaxies are. So this is pretty basic common knowledge that we are inside the Milky Way. So the Milky Way is the name of the galaxy in which we are in, and we know, and this is also a suitable time to introduce something not officially part of the syllabus, but it can be asked, for example, for 1 marks, because this is usually the content of most of the books. So the way that we describe the size of galaxies and of very large celestial objects is we describe them in a unit called light years, right? So if I were to tell the diameter of this, so the diameter of this galaxy in which we are is 100,000 light years, right? So what exactly is a light year? So let me just talk about this. So a light year, as the name says, it's quite self-explanatory. So this is the, so 1 light year, right? So this is the distance traveled by light if it traveled for a year, right? So a common misunderstanding for young eager minds of physics is that we usually on earth we associate year as a unit of time, but when we are talking about interstellar distances we use the word light year, so that seems kind of confusing as to how can time be used to measure distances. So 1 light year is basically the distance traveled by light if it just traveled for 1 year. So fairly simple. So for example, if I wanted to, I can also figure out how much is this distance, right? What 1 light year is equal to. So this is simply the product of the speed of light and the time corresponding to 1 year. So the speed of light is 3 into 10 to the 8. 1 year has 365 days. Each of those days has 24 hours, and each of those days has 3600 seconds. So we can actually come up with a sort of conversion that 1 light year correct to 2SF is 9.5 into 10 to the 10 meters. Again, just a bit of a refresher as to why 2SF, because the least number of SF is the speed of light, which is taken here to be 2SF. So let me just quickly pull up a picture of the Milky Way for you. So here it is. Oh, sorry, not this one. So this is the Milky Way. So if I were to roughly locate where humans are on, so where we are, where our solar system, the sun, the earth, all of these distances obviously seem pale in front of this large distance of 100,000 light years. So you can just imagine how large this distance would be. So we are approximately here at this location in the Milky Way, right? So we aren't really in the center, we are kind of to one side. Now back to the example of stars, and the concept we were talking about is that stars are luminous bodies, right? So the way in which they produce energy is by some sort of a nuclear reaction, which is slightly different for the type of stars we have. But again, that is slightly out of the scope of the syllabus, so let's not indulge in that debate. So stars produce their own light, and this might be a sort of a fun fact for you guys, which is that stars don't just produce light, right? So we know, and collectively we say that stars produce energy, right? or another appropriate term would be to say that stars produce radiation. So for example, if we take the sun, then the sun actually emits three types of radiation, three of the majority type of radiations. So it emits a lot of infrared. This is actually more than 50% of the radiation of the sun. It emits light, which is like almost 35 to 40% of its total radiation, and then it also emits some ultraviolet, right? And this is really small. This is almost 7%. And we'll be continuing this discussion in the lectures to come, which is that the radiation emitted is not just one of those. This is like this entire spectrum which is emitted, right? So whenever we are talking about a star, right, or the power of a star, so we know that, for example, if we talk about the sun is really bright, right? So the sun emits a lot of power. This is why we are told not to directly look at the sun, right? So we know that the sun is very bright. So there must be a sort of a measure in which we can express the brightness or the power of the stars. So the sun is very bright, right? So this is something we know for a fact. So technically speaking, now is the time to introduce a term called luminosity, right? And don't be deceived by the word luminosity. It's not just talking about light. Instead, the way luminosity is defined is this. So this is the total power of radiation. So by saying radiation, we actually don't just talk about light. We instead talk about all of these forms of electromagnetic radiation. So this is the total power of radiation emitted by a star, right? So if we just talk about this quantity, so the symbol of this is L, right? So L for luminosity. Obviously this is power, so it would be scalar, and the units are watts, right? So this is how we characterize what or how powerful a star basically is. So for example, the luminosity of the sun is this. Is 3.9 into 10 to the 26 watts, right? So this is the total power of radiation of the sun. How we got this figure, that will be a debate for another lecture, but anyway, let's just try to take this value as it is for once. And if we think about watt, so what we know is the unit of powers. So we can say that each second 3.9 into 10 to the 26 joules are released, right? So this is the energy generated by the sun in 1 second. And earlier we were also talking about how this energy is actually generated. So we know that this is due to nuclear fusion. So now I have a question for you guys to do. Let's see if you can do this. So this is the question. The sun's output power of 3.90 into 10 to the 26 joules per second is the result of mass energy transfer within the sun. Calculate the rate at which sun is transforming matter into electromagnetic wave energy. So we can simply use the mass defect equation, right? So if we need to find the rate at which the sun is transforming matter, so we basically need to find delta M, right? What is the rate at which mass is being transformed? So this is delta E upon c square. So delta E is 3.9 into 10 to the 26. C is the speed of light, so 3.0 into 10 to the 8 squared. So this turns out to be 4.3 into 10 to the 9, and the units will be kilograms per second, right? Because this was the energy released in 1 second, so this is the mass transformed in 1 second, right? So this is also a question that was asked in a very recent past paper related to this topic. So the next idea we are going to talk about is this. So we know that one of the actually the only major star we know that is also visible that actually has some impact on life on Earth is the Sun, right? So the next closest star to us is actually a star called Proxima Centauri. And as compared to how close the Sun is to us, so this is 250,000 times the distance. So the distance of Earth from this star is 250,000 times the distance of Earth from the Sun, right? So this is how close the next closest star after the Sun. So next closest star after Sun is to us. So the luminosity of this star, so this star has kind of an erratic sort of a behavior as compared to the Sun, because this has some periods in which it flashes very, very brightly, right? So its luminosity is actually much, much, much more than the luminosity of the Sun. And there's actually a picture of this captured by the Hubble telescope, and this looks exactly like how you thought it would. So this is the highest definition picture of Proxima Centauri you could get. So it's pretty much like how we always imagine stars as kids, except for the shape, right? So this is how stars appear in movies as well, right? So this intense flash. So the luminosity of Proxima Centauri is, so it's really much, much greater than the luminosity of the Sun. But any star except the Sun only appears to us as a small speck, right? So it's not very visible. And what is the reason for that? So what I just told you was that this is very bright, right? So this is an image captured from the Hubble telescope, but this is also very, very far from us. So the luminosity, right? Not just the luminosity, the brightness that we see. So let's introduce another term. This is called apparent brightness. This does not just depend on the luminosity. This also depends on the distance that this star or any luminous body is away from us. So the basic idea is this, that light does not just travel in a straight line, right? So light travels out and spreads in space. And this isn't really diffraction, because a lot of the students think that this is diffraction. No, this is just how our space-time fabric is. So what happens is that light doesn't just travel in one linear straight direction. What happens is that it spreads out in space over an increasing area, right? So the more area it gets, it just kind of like expands to occupy that area. So the basic idea is this. So let's say that this is our luminous body, which at its surface has the luminosity L. So when it emits this light, what will happen is that this, and not just light, all types of radiation, this spreads out over an area. So if we talk about area 1, so that is at a distance d from this center of this source. So the luminosity at this point would actually be spread over this area, right? So if you recall what luminosity is, so luminosity is the power, right? So this power would be spread out over this area. So this is a sort of intensity, right? And actually this is called the radiant flux intensity, right? Which is just basically the power incident normally per unit area. So this and apparent brightness mean the same thing. Both of these are alternatively used, but the more appropriate word as with reference to your syllabus is radiant flux intensity. So this is just a short derivation from now, because we know that the power can be written as L, right? So this is the total power of radiation, the luminosity L, and the area can be written as the area of a sphere. So if the radius is d, so the area of the sphere becomes 4 pi d square, right? Because 4 pi r square is the formula for the surface area of the sphere. So 4 pi r square becomes this thing, and d is the radius, so this becomes 4 pi d square. So L upon 4 pi d square is radiant flux intensity. So basically at this same distance from the sphere of d1, the apparent brightness or the radiant flux intensity is the same all throughout. Then similarly at d2, this would be spread over a larger area, right? So this entire circle where the distance from the center is d2, the same radiant flux intensity would be experienced. So if we were to just define this, so the radiant flux intensity is the power incident per unit area, right? So this is intensity of a sort. So we know the basic formula for intensity is power upon area when radiation is normally incident to this area, right? So this thing is important, normally incident. Right, so what we simply do is we take the luminosity, divide by the distance from this luminous source, and we use this formula. So this d is the distance from this luminous source, and then we just use this formula to find out the radiant flux intensity. Now let's have a look at another question which is related to both of these concepts as a whole. So the luminosity of the sun is given. The earth orbits the sun at a mean distance of 1.5 into 10 to the 8 kilometers. Calculate the radiant flux intensity of the sun near to the earth. So if we just need to calculate this, we would just need to use the formula above. So I apologize, I should have told you this. So the symbol for radiant flux intensity is F, right? So F for flux. So F is the symbol. So F equals L upon 4 pi d square is what we would have to use. So L is 3.9 into 10 to the 26. 4 pi remains as it is. This is a constant. And this is 10 to the 8 kilometers. So kilo is 10 to the 3. So 8 plus 3, this becomes 10 to the 11. And we also have a square on top of this. So if you just solve this and give your answer correct to 2SF, so this is 1350, but to 2SF this becomes 1400 watts per meter square. So that sums up this lecture in which we talked about luminosity as well as radiant flux intensity. In the lectures to come, we'll actually talk about how do we know the luminosity of certain stars, and how do the luminosities actually help in finding the radius of the stars. So that was actually one of the questions we posed right at the start of this unit. So if you want to find out the answer to that question, just stay tuned and you'll get the answer soon in the next couple of videos. See you there.